Download this code from codegive.com, link in the description below. Error correction capability refers to the ability of a coding scheme to detect and correct errors that may occur during data transmission or storage. In digital communication and data storage, errors can occur due to various reasons such as noise, interference, or hardware malfunctions. Error correction codes, ECC, are used to ensure the integrity of data by allowing the detection and correction of errors. Key concepts: 1. Error detection versus error correction. Error detection identifies that an error has occurred but does not correct it. Error correction identifies and corrects errors. 2 types of codes. Block codes encode data in fixed size blocks. Convolutional codes encode data streams using a sliding window. Reed-Solomon codes, particularly effective for burst errors. 3. Hamming code, a well-known error-correcting code that can detect up to 2-bit errors and correct 1-bit errors. Hamming code explained. Hamming code is one of the simplest forms of error-correcting codes, which works by adding parity bits to the data. The key steps are: 1. Determine the number of parity bits needed. For m data bits, the number of parity bits r must satisfy. Backslash 2 r backslash gc m plus r plus 1. Backslash 2. Position the parity bits in the data. The positions of the parity bits are powers of 2, 1, 2, 4, 8. 3. Calculate parity values. Each parity bit checks a subset of bits in the code word. The parity is usually calculated such that the total number of ones in the checked bits is even parity. 4. Error detection and correction. When decoding, the receiver can determine if an error has occurred by checking the parity bits and, if necessary, locating and correcting the error. Python code example of hamming code. Here's a simple implementation in Python to demonstrate the encoding and decoding using the hamming 7,4 code, which encodes 4 bits of data into 7 bits. Python def calculate _parity _bits, data _bits. N equals len, data _bits. R equals 0. Calculate the number of parity bits required. While 2rn plus r plus 1. R plus equals 1. Create a list for the final code word with parity bits. Code word equals 0 asterisk, n plus r. Fill the data bits into the code word. J equals 0. For I in range, 1, len, code word, plus 1. If I equals 2j. J plus equals 1. Else. Code word I, 1 equals data _bits I, j, 1. Calculate parity bits. For I in range, r. Parity _position equals 2i. Parity _value equals 0. For j in range, 1, len, code word, plus 1. If j and parity _position. Parity _value caret equals int, code word j, 1, x or operation for parity. Code word parity _position, 1 equals 1 if parity _value else 0. Return.join, code word. Def decode _hamming _code, code word. N equals len, code word. R equals 0. While 2rn. R plus equals 1. Calculate parity bits. Error _position equals 0. For I in range, r. Parity _position equals 2i. Parity _value equals 0. For j in range, 1, len, code word, plus 1. If j and parity _position. Parity _value caret equals int, code word j, 1. if parity underscore value equals 0. Error underscore position plus equals parity underscore position. If error underscore position. Print, F error detected at position, error underscore position. Correct the error. Code word error underscore position, 1 equals 1 if code word error underscore position, 1 equals 0 else 0. Remove parity bits from the code word. Data underscore bits equals. For I in range, 1, and plus 1. If not, I and, 1, and I, equals 0, skip power of 2 positions. Continue. Data underscore bits dot append, code word I, 1. Return dot join, data underscore bits. Example usage. Data underscore bits equals 1011 4 bits of data. Code word equals calculate underscore parity underscore bits, data underscore bits. Print, encoded code word, code word. Simulate an error, flipping the second bit. Code word underscore with underscore error equals list, code word. Code word underscore with underscore error 1 equals 1 if code word underscore with underscore error 1 equals 0 else 0 flip the second bit. Print, code word with error, dot join, code word underscore with underscore error. Decode and correct the code word. Decoded underscore data equals decode underscore Hamming underscore code, code word underscore with underscore error. Print, decoded data, decoded underscore data. Explanation of the code. 1. Encoding, the calculate underscore parity underscore bits function calculates the necessary parity bits and constructs the final code word. 2. Decoding, the decode underscore Hamming underscore code function checks for errors in the code word, identifies their position if any, and corrects the error. 3. Testing, the code includes an example where it encodes a 4-bit input, intentionally introduces an error, and then decodes and corrects the code word. Conclusion. Error correction capability is essential in data transmission and storage systems. Hamming code is a classic example that demonstrates how parity bits can be used to detect and correct single-bit errors. This implementation in Python provides a clear understanding of how Hamming code works in practice.